Alright, draft science, physics, video. Yeah. Okay, I put the camera over here because I don't think I have to show any drawings immediately. Alright, lots of subjects, lots of things I've been thinking about. So anyway, Holiday made a comment somewhere. I won't bother finding the exact comment, but implying that he has an open question that I somehow haven't addressed as to Einstein's prediction of time dilation. And, exactly how Einstein, I have a book on Einstein I haven't read that I probably should. It's awful thick. And, maybe there's something in there that's an actual reference to Einstein explaining what idea came first, bending space or warping time or however you want to look at it. The idea of combining the two concepts that are, in my opinion, only tangentially related, kind of accidentally related. The fact that gravity creates acceleration and acceleration creates velocity, and that velocity has an effect on matter. So I would argue that it was already known, the idea of time change or breaking time barriers was already talked about a lot. From the time they recognized that the light they were seeing from Venus was 7 minutes old or whatever it is, 5 minutes old or whatever, they were looking into the past by seeing something in the sky. They were looking up at the stars and seeing things as they were, not as they are. From the minute that happened, thinkers would think about, well, that's curious. What would happen? Can I go, if I go fast enough, can I just go back into the past? Whether I want to go back in the past or not, it would be a consequence, an automatic consequence of going faster than the speed of light. You couldn't help but crash into the past. Even if you were just trying to win a race and you just decide I want to go faster than, you just couldn't help it, because by doing it, time is such a solid reference, light, the speed of light, is such a solid reference to the passage of time that there's no way you could go faster than light without ending up in the place where the light originated. And the place where the light originates is always the past. Alright. Yeah, so that's, I think, a way to say, so the problem was known. It's a problem that had to have a solution, because you would think it is not unthinkable that somebody like Einstein, who would say something like spooky action at a distance, who was rather convinced that the universe had mechanical bits, that it was a mechanical universe, it could all be understood. That he would understand there has to be a physical process, a physical mechanism that prohibits things from going faster than light. Now, his perception was to think of matter becoming incapable because the space around it would make it heavy. Yeah, but not really heavy in the gravitational sense, if that makes any sense. It's almost an ether idea, in the sense that there's this restriction in the fiber of the structure of space that prevents matter from going too fast. So anyway, the bottom line is, he calculated it as a mass equation, essentially, and just said, well, I'll take your mass and I'll multiply it by recognizing the force of it. So if I give mass velocity, we know it has more energy. It can do more damage. The wrecking ball, the faster you move it, the more things it breaks. The bowling ball, the faster you roll it, the more pins it knocks down. That kind of idea. And basically turned it into a mass equation. So the faster you go, the heavier you get, that way nothing could ever push you. So by the time you're going near the speed of light, your physical body becomes as heavy as the universe, and there's not enough energy in the universe to push you because you got so heavy. Now, it's not a terrible way to look at it, and again, it fits in his bent space idea that space is the thing controlling, the wrong word, it's connected to the function of force, at least the big force of gravity, or mass. So it's related to mass. Time ends up being related to mass. So that's how the two get connected together. Now, my argument to you is that I obviously have now found an explanation that does the same thing. It creates the terminal point where you can't go any faster, in the sense that instead of getting so heavy, you get so light. You get invisible. You get impossible to hit. Everything about you is already going. As you start to move the speed of light, I can't create any force that can actually hit you anymore, essentially, because you're getting thinner and thinner and thinner. And I just can't hit the target anymore from behind to make you go faster. So it's the same speed limit, and it's just based on a different perception that the change isn't in the space, the change is in the thing moving. Okay, so its velocity is a symptom of an imbalance in the matter, and that imbalance is reflected in the sense that the matter is converting, in a sense, into force. You're being there's probably a better word for it. I'm just trying to find a word of, you're being morphed from matter into energy as you gain velocity. You're transitioning. Okay, and it takes a long time because yes, the speed of light is very fast and we move very slow. So yeah, we're a long way from the full transformation if we're going 50 miles an hour. So he posted a couple of videos. One was a reference to an old 1950s kind of science documentaries provided on the idea of frames of reference, and that all has to do with mechanical things moving, our kind of speeds. And so it doesn't really relate to the references we're talking about when it comes to the speed of light and how you can perceive things in the universe, how you can sense them. And we know that we sense through light, but when you're just watching, these mechanical objects can move, and the light isn't relevant because the movement won't be challenging the speed of light in any way. But we do know if I move this fast enough, I can't see it anymore. My brain, neither my brain or the photons, I don't have enough photons to make resolution. So I lose sight of this. And if I put a strobe on where the light is regulated, then I can see it again. As a thing, instead of a blur. So our ability to So the relevance of the speed of light becomes really relevant when you're talking about very fast speeds, because now the light itself is a player in the sense that it will create distortion. So when things are moving slow, light isn't creating much distortion, but like I've pointed out, it can create some. But when you're getting into these really fast speeds, then the light itself is corrupted. And you can't even really have a conversation about what you're going to see, because you're not going to be able to use light anymore as a mechanism to see something. It won't work. Things won't reflect the same way. As I sort of kind of pointed out, if the train's moving forward towards me at the speed of light and I shine light on it to see it, well, the point is the train's going to reflect X-rays back at me. It's not going to reflect the light I sent back at me. So I could send white visible light onto the train, And the train's going to reflect it back at me as X-rays. I think it's just a rational consequence of the fact that the emitter matters. How fast the emitter is moving and how fast the receiver is moving and which way they're moving will change what you see. And likewise, if I'm on the back of a train moving half the speed of light, everything is going to go red. Everything's going to get stretched in terms of how I'm going to receive it, because I'm going to keep running away from the bullets, essentially. So they're going to have half the effect, kind of a thing. I mean, if a bullet, say, is moving 500 miles an hour, I mean, I know they're more like 5,000, but let's just say it's moving 500, and you're moving 300 miles away from it, you know it's only going to hit you at 200. It's going to be a pretty slow bullet. You know, this is stuff we know, and we know it from mechanics. Alright, so I don't know what kind of argument you want me to make. You're going to claim that Einstein predicted out of nowhere, and therefore Einstein is valid because how could he possibly have known? And what I'm going to argue is the context of Einstein's understanding is in dispute here. What he already thought about, what conditions he knew any theory he wrote had to meet. These are conditions he already knew existed, and he theorized in that envelope, just as I theorize in the envelope of known facts. I'm not going to come up with I'm not going to sit here on the internet and make an argument for a theory that says the moon is a cube. I'm not going to do that because I know it's not true. I know I have to conform a theory of the universe where the moon's a sphere. And Einstein did the same thing. So I'm not saying Einstein wasn't impressive, but what I'm saying is he of course built the theory in the context of the world existing, and in a sense wanting to explain as much of it as possible with whatever mechanism he was using. And the fact is that when you mix space and time, they have something in common, which is velocity. Well, let me say, when you mix gravity and time, they have the common element, which is velocity, produced by acceleration. Can't get it any other way. I mean, acceleration is fundamentally the mechanism of gravity. The consequence of gravity is, of course, velocity, and velocity is related to time. And the prohibition against getting anywhere near the speed of light. So anyway, so my argument is that's, I think, so much more sensible than warping the conditions of space, when all you have to recognize is you're converting matter, moving in 3 dimensions, into force, moving in 1 dimension. And that's what's happening as you approach the speed of light. You're not matter anymore. You're force, fundamentally and primarily. Alright, so I hope that answers your question, or whatever the appeal to authority element that's in it. I don't know exactly. You know, this, like I said, is these you know, this perception of almost like the Nostradamus kind of thing. Like, because you get something right, it means you got everything right, and you understood everything. And it's, you know, there's a little bit of that goes on here. And because quantum mechanics describes 3 things, then it describes 300 or 3 million. And I'm going to argue that's a lot of this is just that. It's a fool's authority, like fool's gold. Okay, you got a lot of fool's authority here, and all of these underlying premises are suitably questioned, skeptical, highly skeptical. All right, so yeah, so I'm basically, look, it is ludicrous to have a conversation, in my opinion, about what a flashlight's going to do when it's moving the speed of light. Because either by Einstein rules or by my rules, it's not a flashlight anymore. I mean, you can sort of understand if the flashlight weighs as much as half the universe, let's say, it's probably not a flashlight anymore. I mean, it probably isn't going to be producing light. Yeah. Anyway. Yeah, I mean, that just got me thinking about how, you know, there's so much inconsistency in the sellers of quantum mechanics. You know, one will tell you that the whole light thing with black holes is just bullshit. Light can't get trapped in a black hole. You can't pull light back into a black hole with gravity, and you know, they'll talk like that, like a Susskind or something. They'll say, no, there's no light being pulled back into black holes. I think he says that in somewhere. And then they got this Nemo guy, or whatever his name is, that Holiday keeps playing, and he's saying exactly the opposite. He's saying, oh yeah, light can't escape. Yeah. And I think people can just intuitively understand. There's absolutely no evidence that light slows down, escaping even the Earth's gravity. Not the least little bit. Light doesn't slow down in gravity. You can't pull it back with gravity. It's not affected. It doesn't go faster into gravity. These are just facts. Forces can't be affected by forces. They can only be deflected by matter. That's how simple this is. The theory is that simple. There's just nothing, this isn't complicated. Force does not mix with force. Alright, so that gets me to another subject. I mean, there's just so much of this, right now. There's just so many things in my mind. I just love this tube thing, right? It's just got my brain really thinking. You know, because it's just such a bullshit little effect. Because the angles are so different. The light you're seeing in one of those circles is coming out at like 6 degrees. I mean, it's pretty straight out of the tube. And the angle that's reflecting, creating the next ring you see, is huge. It's like 45 degrees. So it's the same surface is creating two reflections at completely different angles. I mean, disparagingly different. That's bothering me. But it's kind of like that double rainbow thing, right? I mean, the first rainbow is at whatever, 42 degrees or something, and the second one's like 18 degrees different. But this is more than 18 degrees difference, I think. But you know, maybe not. I have to look into it. All right. So the other thing is diffraction gratings. So Holiday posted a link to this video and he titled it "Proof Wave Nature of Light. Where does the light go in Mendham?" ? Now, I don't think there's any question in the video about where light goes, so that's kind of funny. And I have the interferometers drawn here. So I don't even know how that. I don't know how that's even related to the question. I don't know how there's a question regarding where the light goes. It's like in the double slit experiment. In my opinion, there's no question where the light goes. Okay, where the light isn't, the dark places, it isn't light plus light equals dark. It's that, no, the light went to the neighbor. The bands are twice as bright as if the light had filled the whole thing. The same amount of light is being produced. It's just that it's now in different segments. And so anyway, this video uses the interferometer. The interferometer is supposed to be the name of the whole setup with the mirrors, but they call the little beam splitter, they call them interferometers, which confuses everything. So I am thinking of trying to buy one of those, a decent one, but I found out they might be in LCD projectors. So I was thinking, you know, the video projectors that use LCDs. So I was thinking of buying a broken one, but you can get broken ones for 20 bucks. And, there might be a $60 interferometer in there. But anyway, but it depends on the quality, of course. Want one that's decent. But, it'd be fun to play with them. But anyway, the idea is, so I looked into it a little bit. It's basically two prisms. So it turns out to be a cube. And they have a surface in the middle that is acting like the mirror. But they don't use metal if they can avoid it. They use, different resins to create the reflective surface. Because they're trying to avoid the refractive index kind of thing happening. So the idea is, when light hits a surface at an angle, some of it goes, the idea is to get the light to go through in, but not to bend as it goes in. So that's the tricky part. And I don't think they really can avoid that. So technically, the interferometer, I don't think, is producing output that's exactly at the right angles. It's being bent a little. Because it's going through a big piece of glass, actually. Anyway, and it has a surface problem. I mean, it's transitioning between surfaces, which is always a problem in terms of changing the polarization and creating refraction. A change in the reflective index creates a change in the light transmitted through. The light reflected does okay, but the light transmitted through, the angle changes a little, like in a prism. Okay, anyway. So the idea is that these beam splitters are basically just half mirrored, is the concept. And and there's lots of different ways they do that. Really thin coatings, blah blah blah. But what that really is a diffraction grating. Either a diffraction grating, like I've never seen where you can buy one that's made out of little tiny holes, but that might be interesting. Just random little holes. These, the ones I have, are made of lines. So there's lots of vertical or horizontal lines. I mean, depending on which way you turn it. So yeah, I would argue that the beam splitter is a two-slit experiment, right? And it's not a two-slit experiment, it's a diffraction grating. So it's a 500 slit experiment. That's what's happening to the light. So the ringed pattern isn't being created by the phase difference in the light and constructive and destructive interference between the two beams being focused back together or forced back together. It's being created by the diffraction grating. Oh shit. Yeah, I just lost my diffraction grating. I have to get a flashlight. See where I dropped it. Let's see. Ooh, this flashlight's getting dull. I don't see it. Ooh. Well, anyway. Anyway, I don't really need it. I wasn't going to show you with a visual. I was just going to show you with the visual in the sense that what I did. So what I noticed with this, so this is incredibly thin, as you can see, just, a little piece of plastic. Alright, so it has lines going in one way. So I was playing with it, like a polarizing filter. I was seeing what happens when you turn it and do different things. And so what I found, I was very curious, is that what essentially happens is, so the first one creates what the aligned diffraction should be dots. Okay, 3 really easy to see ones, then the other ones they get duller pretty rapidly, and they get pretty harshly duller. So you see 3 hard ones. This is 500 lines. And so what I found that was incredibly interesting is when I had them lined up the same way and I moved them, I found the 3 dots stayed exactly where they are. And the only thing that happened was 3 more dots moved. So when I moved one piece, it made a new pattern, and the new pattern moved. So the obvious conclusion out of that is that the first film, we know that the two-slit experiment, we know that the interference pattern, or whatever the pattern is created right on the surface. It happens immediately. I mean, it happens so quickly, the interference pattern develops. So the little microwaves or whatever that's happening, it's happening so quickly in so little tiny space that when I had these two plastic films stuck next to each other, I still couldn't catch the light before it was interfered with. So the first pattern was created by this film, and it just got transmitted through the second one. And so it spread each one of the little dots a little tiny bit, create a little tiny pattern in each one of the dots from the first one, and then the rest of the beam that wasn't affected, that didn't get interfered with, right? So there was a whole portion of the beam that never had any interference. The stuff that went through the middle, there's no constructive or destructive or anything. It's clean. And it went straight through, hit the second film, and created a second pattern that was probably 50% as bright. Maybe 60, I don't know. It was perfectly visible. It just wasn't as bright as the first pattern. So what I'm saying is this created one sheet creates a normal 3-dot diffraction pattern. A second sheet creates another 3-dot diffraction pattern and does a little bit of diffracting to the original pattern. And like I said, the consequence of that is that the first diffraction, the first interference pattern, so the light photons had to interfere with each other right on the surface, which indicates, I'm just saying, it seems to indicate, okay, that maybe the interference, the cause of the effect, is really in between the slits. It's happening there, not later. Not on its way to the target. It's not happening on the way to the target. It's happening right on that surface. So I'm just saying that seems interesting is all. I'm just saying. I mean, maybe the micro tiny bit of distance between the two pieces of plastic film is somehow sufficient to create the entire Huygens effect. But I'm just saying it is curious. Yeah, it surprised me because I thought if I doubled the lines by putting two films together, I would end up with two, almost like 1,000 lines. And instead of getting the 1,000 line pattern, I just got two 500 line patterns. Interesting. I think very interesting. So I have to try separating them. So if there's distance between them, I'll have to see what that effect is. So yeah, that's just a just one of the thoughts that's running through my head. All right, so I'll play a little of this video, and like I said, I don't really understand why Hothloday is making this claim, proof of the wave nature, and where does the light go? Because this one really, I think in one of his other laser. See, the problem with these are really good videos, but he's doing them for instructional purposes, and so instead of he leaves there, I'm not going to tell you what the wavelength is, or I'm not going to tell you what the distance, because we're supposed to figure it out. And I just hate that crap. I'm not listening to this crap because I want to solve math problems. I want to just know the relationship. So just give me the fucking answer so I can understand. Oh, okay, the slit's wider, the pattern's smaller. Okay, let me know the answer so I can put it in my brain and understand it. I don't want to waste my time finding out for myself. It's a waste of my time. I don't need to do that. Alright, so it's an interferometer experiment. So these lights go blinky in different, this one goes on, that one goes off, but they're actually both on at some time. So you can see they're both on there. And, one goes off, one goes on. So it's completely, it's not like it's all or nothing. So that's one point to make.
look at the intensities in these two spots.
All right.
As I
so he presses on the table to change the difference.
To change the path length difference in the two arms of the interferometer.
Right.
As you can see, as I press on the table, that when the spot on the right goes dark, the spot on the left is bright. And then
Yeah, well, see, it's just not at all perfect. Both of them shine sometimes, and both of them are out sometimes.
And when the spot on the left,
Let's see if I can catch it with both out.
the
So
spot on
far,
the
no.
right is bright. So you can see that they alternate.
Okay, well, it seems pretty clear they alternate,
Now do it
and
again.
that you can
And
balance
spot
them,
on the
though.
left,
But you can't create a nothing. There's no nothing here.
is dark, the spot on the right is bright, and then when the one on the
Yes, we got that part. Okay.
the other one is bright.
Back
So
to
you
the...
can see
All right, so here's the quick explanation. I mean, obviously it has a lot of U-turns in it that are unnecessary for anything. So the laser comes out here, reflects, go through a lens to be widened, and then it goes off a mirror and then through two interferometers. So the first interferometer, well, this is the second one he added, but I'm just saying the first one basically, so the beam goes through, goes straight here, bounces off this mirror back here, goes out to the laser here. This one bounces off here, comes through here, goes to that same laser, and then the second interferometer bounces out here and shows the second pattern. So what was posed, let's see if he poses, no, he already had the second interferometer, but I'm just saying that the question was posed, okay, we know light goes back, because that's when it's dark. The dark light is ended up going back into the laser. So that's why you put the second interferometers, basically catching the light coming back out of the experiment and bouncing that over here. So that's the light escaping. So when it went dark in the past, it was like, where'd the light go? And the answer is the light was going back into the laser. So now we know that because the second interferometer is there. All right.
the intensities alternate. This implies that when we have constructive interference in one beam, we have destructive interference in the other beam, and vice versa. Now, in order to see the effect even better, I'm going to take this mirror and change and move it backwards so I can change the length of one of the arms so we can get back to the rings.
So this is creating the, it's really doesn't make any sense, because if it was destructive and constructive interference, you couldn't make a solid beam. But anyway.
Now, as we see on the screen in close-up, we see the effect even more dramatically. The spot on the right is our normal beam that leaves the interferometer.
So he had to move it a whole bunch to get this pattern to show up, and yet just barely touching the table makes the whole thing blink, which doesn't make much sense. If it was that sensitive, why does he have to move it a whole bunch of distance to get the pattern? So my argument here is that when he moves distance, what he's really doing he's taking this centerpiece and bringing it forward. So he's changing the focus. So this ring is getting lost, and all you're really seeing is the center. So it's just the centers on, centers off. And so the ring is just a consequence of him pulling back, which is letting more of the light, whatever you want to call it, in. So technically it wasn't constructive and destructive interference when he had the focus only on this center.
The spot on the left is the one that
See, so this doesn't make much sense, because this is light, this is dark. You've got the second ring as light, but they don't really line up too well. And then look at the third ring. The third ring is half and half on both. That shouldn't be possible. If they were truly out of phase light frequencies, then it would be on, off, on, off. It wouldn't be on, off, off, on, and then both on halfway. That wouldn't happen.
Associated with the beam going back into the source. Now I think you can see it here very clearly that when the central fringe is dark in one arm, is in one spot, you can see that on the other spot it's opposite. So when it's dark in one, it's bright in the other. When it's bright in one, it's dark.
Except for the outside rings that are dark in both.
In the other.
I mean, light in both.
This is a very even more dramatic way of showing it. So we've seen that when no light comes out of the interferometer, all the light goes back into the source, which means that when we have destructive interference in one beam, we have constructive interference in the other beam. The puzzle is that in order to get destructive interference, it means that the path length difference between the two arms must be either a half wavelength of light or odd multiples of half wavelength of light. Now, if indeed the path length difference is half wavelength of light, then why isn't there destructive interference in the beam going back into the source?
See, I really don't understand the question entirely. Why isn't there destructive, even more destructive interference? I mean, putting two interferometers in an experiment, I'm sorry.
Because the paths are identical.
It's already...
So the puzzle I want to leave you with to think about is how's that we get constructive interference in one beam and destructive interference in the other beam when the two paths are indeed the same in both cases.
Okay, well, my first argument would be is that this isn't about the paths. The interference is being created by the half mirror. Okay, that's creating the holes. That's creating the diffraction grating. That's causing the effect. But anyway, here's the quick drawing of what's going on. Yeah, I know. This will be... I don't know if you're going to get this. Well, anyway, the light goes in. Okay, so that's a little line here. And what I've done is put little circles here indicating how many times the light goes through. Okay, so the light going through is a refraction. The light reflecting is a reflection. So that's sort of the difference, is if you calculate how many refractions there are versus how many reflections. So, but anyway, this doesn't matter. So this is the true interferometer here. So here's your two arms, and in theory, you know, when you make them a half wavelength different, then you should have full interference. And these are just, I didn't bend the targets or put the target through lenses. I'm just saying here's the two targets that you're looking at. So these are the ones that they were visualizing. The trick is, you put this second one in here to trap what goes back, but it only traps half of what comes back because it's still an interferometer. So there's still these arrows, half of what comes out of here ends up going back into the laser. So you don't stop the black backflow by putting another interferometer in the way. You just cut down the intensity of it. So it doesn't really improve anything. Okay, well anyway, the key numbers is that in this original pattern, it's an equal number of refractions. Both beams get refracted, that is, they go through the square 2 times. First here, and then here, 1 time. 1 time in different intervals, of course. But it's both 2 and 2. The beam here ends up being 1 and 3. This one goes through the refracting process, goes through the mirror only once. And this one goes through the mirror 3 times. And the stuff coming out is 2 and 4. So there's a lot, there's a huge unevenness in the lengths might be the same, but what went through the mirror and what reflected is very different. So that would be part of the argument, I would say. But I mean, I have to look into this whole, these interferometer things, because like I said, I think it's, you know, it's kind of suspect. There's so many ways to make one, but you know, just draw a quick picture. But the idea is you have a glass cube, and they just put a thin layer and they try to use non-metallics to create the reflector. And the light either reflects or it goes through. So it's a 50, they want it to be 50-50. It doesn't really turn out to be that way because this surface absorbs some of the light. So you end up with more going through than you end up with reflected. But anyway, but yeah, no matter what you do, you're creating a diffraction grating of sorts. And there's no way around that. That's the 50-50 part. The light either goes through or it doesn't go through, and if it goes through, it means it went through something that has little holes in it. Slits. So, now why there's the shape of Newton's rings, that part I haven't figured out yet. But he puts the laser through two different lenses, and they're compound lenses, so I'm not exactly sure what they're doing. I mean, the argument is they're just magnifying the image so you can see it, but I don't know. So it's reasonable to question. Yeah, so that's, I don't know what you want as a response, but I don't think this is proof of wave nature, certainly. And asking me where the light goes, I'm just saying there's no unaccounted for light. I mean, the biggest where does it go is, the funny part is because he put the second interferometer in, he must have increased, when he did that, he didn't tell us, but he must have increased the intensity of the laser, because he was throwing away 50% of the light right here. I mean, this interferometer is reflecting half the light right off the bat. So half the light that goes into the experiment gets wiped out by this second interferometer, and there's no mirror here. It's not put back in. So I'm just saying that this first beam splitter, 4-way beam splitter. Yeah, so I don't know I don't know the nature of your question. Where does the light go? What light is lost? And so anyway, yeah, that's probably enough on that. So was there anything else I wanted to take care of? I think the important one was because I'd like to have a conversation about all the paradoxes created by the relativity crud, and why it's so much simpler just to recognize that velocity is what creates the change in function. And it's the change in function that you're recognizing. Clocks don't work the same. It's like when muons, I mean, they're almost giving it away in a sense, right? So you have a radioactive particle, and it decays slower when it gets hit by a cosmic ray, and it accelerates. And so it decays slower. Do you really think it's in a time paradox? Do you think that it's really time traveling or something? It's actually in a slower universe or something? Or would it make more sense to just say it doesn't decay as fast because it's moving very fast, which means the mechanism inside of it is changed? People lifting off in rocket ships don't drink tea with their pinkies out because it's physically stressful. How else to say? But that's acceleration. And acceleration is certainly physically stressful. But velocity, although not as physically stressful because we never have huge velocities, so we can't know for sure. But yeah, it's not as physically stressful as acceleration. But yeah, so do you really think that? Do you really think that the muons are decaying slower because they're in a time warp? Come on. Or do you think it makes more sense to say their physical structure changes, like bullets change, when you shoot them really fast? When they're traveling fast, their internal mechanisms change. The velocity is part of who they are. who they become. And the new thing they are, because of that velocity, doesn't decay as fast. I mean, I think the simple metaphor of the dancing thing, you know, if you have a structure, a routine, no matter what your routine, just me doing this video, and if I said, Gary, say the word banana every 5th word, I now have to say banana every 5th banana word, and therefore banana, you could see how everything I'm saying is slowing down because the bananas are getting in the way. Yeah. Anyway. Alright, so, but these, you know, they're interesting subjects, and, you know, I just think, I know, I mean, Toffolidae sort of raised the point. I mean, what, oh, Gary's questions every single guest science ever made, and yeah, it is kind of ironic that I think that it appears like every big question that fell into physics' lap, it got wrong. I mean, Benjamin Franklin got plus and minus wrong. You know, Einstein getting, you know, push-pull wrong. You know, time dilation also, but whatever. You know, you can almost argue that that went back further, but it doesn't really matter. You know, wave, particle. I mean, it's just, you know, it is funny now that, you know, that that stupid Nemo guy says something like, well, yeah, you know, they are particles, but they're not. You know, what's the point of calling them particles when they're not going to have any of the properties of particles? It's like calling them waves when they don't have any of the properties of a wave. It's like they're using these words and it just doesn't mean anything because they really don't mean it. You know. And you know, yeah, that was another thing I found really obnoxious about Toffolidae posting this crap. There's a guy saying that this, you know, quantum mechanics proves there's no determinism. It just ends all that conversation together. It's all over. You know, there's true randomness. How would he know it's true randomness? And he even uses rolling dice as an example, as a metaphor. And you're almost like arguing, well, you're a physicist. You know that rolling dice isn't truly random. So again, I'm going to argue that the one thing in the universe that's truly random is the one place we can't see. Isn't that curious? I mean, nobody should be at all skeptical that it just happens that the one place we can't see is the one place where truly random shows its face. You know, and that it doesn't happen on any of the bigger things that we could actually see. Like there's not truly random. No one thinks there's truly. I don't think anybody really thinks electrons fly truly randomly. Well, I don't think they do. I don't think people could be that stupid. Well, maybe they can. Anyway, it's so dumb. Anyway, and no one ever talks about aiming something as a simple way of fixing the paradox of measurement. You don't have to measure something if you already know where it's going. So just get a Google car, okay, and you'll know exactly where it's going, okay, and then to see if it gets bent by anything and truly randomizes. This is such bullshit. Anyway, so anyway, till next time. I think it's enough. I got tired all of a sudden, but yeah, so I have lots of experiments to do, and it just takes time. I've got to set it up, you know, and got to get the laser pointed right, and then you have to get all this stuff pointed, and you got to do it, you know, and got to find my clay, because I was thinking clay would be a good thing to stick things into. Anyway, take a go look for that. Finding good things to, you know, and then I always stack things on boxes, and the box gets crooked, or it gets heavy on one side, or tips over. I mean, you know, I need a laboratory. That's what I need, a laboratory. So I could be truly mad scientist and such. Anyway, till next time. I think that's it. I think there was something else I wanted to do, but it can wait till next time. So, till next time.